Hello, guys. Today I'm going to share a very interesting paper that was published at the SLR conference last year. It is titled as EUREKA, Human-Level Reward Design via Coding Large Language Models. This work is conducted by the research groups from NVIDIA and other academic institutions. In this work, they utilize the large language models to generate and revise the reward functions in the reinforcement learning algorithms to solve several complex manipulation tasks, including the texture manipulations. It utilized the generation, code writing, and in-context improvement capabilities of GPT-4 to explicitly write the reward functions. And it also enables a new gradient-free in-context learning approach to incorporate the human feedback into the deep reinforcement learning algorithms in order to improve the quality and safety of the learned behaviors. It conducted extensive experiments, and the results shows that the EUREKA outperforms human-designed rewards on 83% of these tasks. And it also demonstrates for the first time that very complex texture manipulation tasks that was impossible to be learned with manual rewards can be learned with EUREKA rewards. Okay, let's look in details. First, let's look at the method in EUREKA. There are three key components in the EUREKA. The first component is an initial reward generation components in order to generate the reward functions with the source code from environments and the task descriptions. After generating the initial rewards, it can be buggy and be suboptimal. So they use an evolutionary search algorithms to generate several candidates and select the best reward functions according to their performance on the training environments. And after after selecting the optimal rewards from several candidates, and it also utilizes a reward reflection components to revise and modify the reward functions with large language models. So let's then look in detail how these three components works. Okay, first, they utilize the source code from the environment as context to prompt the LLM to generate proper reward functions for specific tasks. The initial reward prompts, user prompts are shown as follows. So, as I mentioned before, it requires a task observation code string and the task description in their user prompts. The environment context code is the essential variables that are needed to compute the observations in the environments, and the task description is a description to describe the tasks, of course. Okay. And then they use a task agnostic prompts to generate the reward functions. As shown here, it did not specify some components for specific tasks. Instead, it only utilized format code description to describe the essential components in their reward function and the return variables for their reward functions. And also, you can read the generated reward functions from the large language models in their website here. They did a very excellent job to show the best EUREKA rewards in the website, and if you can just click on these tasks and you can see these rewards. Okay. As I mentioned before, the initial generated reward functions from the large language models could be buggy or suboptimal. So it requires several steps to or several rounds to be optimized. So they design an evolutionary search mechanism to decrease the probabilities of buggy reward functions and to improve the qualities of the reward functions. Specifically, they generate 16 candidates reward functions for each tasks in the beginning, and then they run these reward functions in the training algorithms in the training environments and get the sparse feedback from the environment. That is the success rate or some penalty terms that can be the ground truth sparse reward from the environments. Then they select the best performant reward functions from the with the sparse rewards. And after that, they also design a reward reflection module to modify the reward functions according to the history generated reward functions from the large language models. Specifically, the EUREKA reward functions are asked to expose their individual components in the reward programs, and the reward reflection components track the scalar values of all reward components and the task fitness function during the training process. And then they prompt the large language models to change the hyperparameters or change function forms or adding or deleting some components in the reward functions. Okay, then let's look at the experiment result. In this paper, they really did extensive experiments, consist of 10 distinct robots and 29 tasks with the ASAC gym simulators. As shown in Figure 4, the EUREKA outperforms human-designed rewards, that is the purple line, and also it outperforms the L2R reward functions in these tasks, and the average success rate is apparently has an apparent improvement over the L2R algorithms, the human-designed reward functions, and also the sparse rewards. And also, we could see that in some complex tasks such as Franca cabinet, the ANT tasks, the EUREKA function also could have more performant rewards has better performance compared with the human designed rewards and the L2R rewards. In Figure 5, they show the consistent improvement of EUREKA functions with multi-round improvement of the reward functions. For example, in the detectability tasks, with 5 iterations of EUREKA update improvement of their reward functions, the success rate can be improved from the 30% to 50%, and can be improved over the human designed reward functions, and which is task agnostic, and I think they can save much human labors. And and they also show the initial reward functions influence on the final performance, as shown in Figure 8. They demonstrate the performance with EUREKA rewards, as shown in the blue column, and the human designed reward, the right column, and the EUREKA reward function, but with human initialed reward functions, and shown as the green. Apparently, with the initial human designed reward functions, the EUREKA rewards can be improved by a large margin over these 5 tasks. And it also shows that the huge potential of EUREKA to improve the human designed reward functions. Okay, they also show when align the EUREKA rewards with the human feedback, they can see from the experiment result that the agent trained with EUREKA acquires a safer and more stable behaviors as instructed by the human. Okay, that's all for this work, and let's make conclusions. First, EUREKA demonstrates the zero-shot generation, code writing, and in-context improvement capabilities of GPT-4. And when they are utilized to design explicit reward functions, the initial reward functions are very essential. And when it is provided by the human, it can be improved by a large margin. And the multi-round improvement are also essential for domain-specific tasks, because the GPT-4 is designed for the common tasks. So when you want to utilize it for domain-specific tasks, you need to improve the reward functions step by step. And I think this work is because it needs the environment source code. So Now the simulators, there are huge gaps between the simulators and the reality. So I believe this work can have a broader impact with the advances of simulators. But now when you train robot policies in the simulators, it also costs much efforts to deploy your policies into the reality with sim to real techniques. And also, I have a question for this paper, because I observed that it is very hard to incorporate domain-specific domain-specific data to improve the reward functions. So maybe in more specific tasks, it is better to incorporate these domain-specific data to improve the reward functions. Okay, that's all. Thank you. Bye.